All right. Let's get started. It is 1:40. All right, this is buildingdevelopers.google.com on Google App Engine. This is an App Engine talk. Make sure you're in the right place. I'm Dan Sanderson. I'm a developer programs engineer at Google. I've been at Google for about 6.5 years. I worked on the App Engine team for about a few years, from 2008 to 2011. And since 2011, I've been working on the Google Developers website. That's developers.google.com. How many of you have seen the Google Developers website? Excellent, I thought so. I've also written this book, Programming Google App Engine, published by O'Reilly, currently in its second edition. The second edition came out last October. I hope you get a chance to take a look at that. I want to talk about Google Developers today. The Google Developers website is an App Engine application. It's written in Python. And in the last 2 years, from 2011 to today, we've built out a website with a bunch of different features. We have a content management system that hosts all the technical documentation that's on the website. We have an events calendar, the developer showcase, the Google Developer Groups home pages, the Google Developers Live with all the live streaming video, and of course the Google I/O website. I want to talk about how we built this website on App Engine, but I wanted to get pretty specific. I want to talk about the App Engine details. And so I'm going to focus on a very specific part of the website. We're going to talk about just a piece of the content management system. Of course, content management has a bunch of different parts to it, the static content build, publishing workflows, that sort of thing. But I want to talk about kind of the App Engine specific parts of that. So we're going to just take a part of that and talk about it today. The design that I want to talk about is the design we actually use. It's a pretty straightforward design pattern you've probably seen before, and we'll talk about how that gets implemented on App Engine. And I'm going to focus on the App Engine-y bits with regards to the implementation, so we don't get distracted by other parts of it. If you have any questions about anything that I haven't talked about, feel free to find me later and we can talk about it. I'm happy to talk about the implementation. We'll also talk about how this is implemented, what tools we use, what libraries we use. And here I'm a little bit conflicted. We have been working on this website for a couple of years, and App Engine has changed quite a bit in the last 2 years. There are quite a few new tools, libraries, and services that have changed some of the best practices on how you actually build these things with App Engine. So many of the things we actually do with real code are a little bit out of date in terms of best practices. I would love to just show you the real thing, the real world code. It's messy, it's long, but it's also been tested and runs the real thing. But I think I would be doing a disservice if I didn't acknowledge the new libraries and tools that have been developed. So we're going to take a hybrid approach with this talk, and we're going to take the design I actually use, but we'll use a modern implementation. We'll talk about how to build it with the modern stuff. We'll use examples in Python. And I'll try to call out discrepancies between the real implementation and what I'm talking about as I have time. Again, if you have questions more about like what we actually do and the sort of hairy details, just let me know. And I'll try to call out alternative designs as we can. But we have a lot of material to go through, so I'm probably going to be rushing through a lot of it. So let's sketch out a content management system just to work with here. We want the content managed separately from other parts of the website. That's kind of what a content management system means, is that there's other stuff going on the website. So this is software built into the app, and content publishers, content developers are going to be interacting with the software to get the content onto the website. This is going to be a file-based CMS. A lot of people, when they think of CMS, they think of editing text in text areas in a web form. For technical documentation, we have content developers that are editing lots of different files with lots of regular structure. And so they're going to be using local files for that and then uploading them to the website using a client tool. So there's going to be a client-server interaction in this design. Content developers are making a lot of changes all at once. Basically, they're developing, writing the content for a new release of a new feature, and then they want all of it to go up at once. So they have a lot of changes to represent, potentially over many files, possibly hundreds or even thousands of files. We don't want just anyone publishing to our website, so of course we have access controls for this client-server interaction. When we think about the design, we're going to try to accommodate fast file serving. Obviously, that's just a general requirement that we want, but we're going to need to think about that when we do our data modeling and things like that. Most importantly, the usage model here is we have many content developers working on different parts of the website concurrently, so we're going to need to accommodate that as we work through this. So if we just imagine a client of some kind, let's say a command line tool that's passed a set of files. I've got my files on my desktop and I want to get them to the website, so let's just start with here. I've got a publish command and I want this publish command to get these files onto the website. Well, we've got a client-server interaction. why don't we just do this? The client tool uploads the files to the server. It could do it one at a time. It can call an upload endpoint on the server, and then the server takes those things and puts them on the website. The payload would just be a URL path and a content type in the data block, and then the server installs it so that when people come and ask for that URL path, they serve that data with that content type. I'll wave my hand over the part where the client figures out what the URL path and the content type are. You can imagine different ways of doing that. Internally, we just use directory structure conventions for that in our revision control repository to figure out what the content root is. So this is great. Actually, this gets us most of what we want, right? We can get files onto the website. We can create new paths. We can update existing paths. Now, usually with data, you want to do a third thing. You've got create, you've got update, and of course, we are going to want to be able to delete paths as well. You can imagine that maybe the client can just issue delete commands in addition to upload commands. But that would require that the client has to maintain some kind of internal notion of what is on the server. It has to know what to delete in order to do that. And that's a lot of work and can get kind of messy. So the client knows what it has. The server knows what it has. Why don't we just make the server do the work? So the client just needs to say, this is what I have. Do what is necessary. And so we'll just add a new request in here, a new call. It's a start call. It says, OK, this is what I have. Please do what you need to do. And also, these are the files I'm uploading. So this is the client's opportunity to say that. And then the server can turn around and figure out what it needs to do. Now, each content developer is working on a different part of the website. So they're probably not going to have a complete view, up-to-date view of the entire website in their local files. So it's not quite sufficient to say, this is what I have for the entire website, do what's necessary. So we have a notion of projects. And in this case, projects are just subpaths. So if I'm a content developer working on, say, the App Engine documentation, I've got local files under /App Engine. And I have a complete up-to-date view of what App Engine docs look like. That's what I want to upload. So our protocol just has the start request says, this is the project I'm working on. These are the project roots. And these are the files that I have in this project root. Please do the right thing. Then the server says, oh, you've got A, B, and D. Well, I've got A, B, and C. So I guess I should be deleting C. And you'll be giving me the uploads for A, B, and D later. So great. We've got a way to synchronize the state of the client onto the server. I'm not entirely happy with this diagram, mostly because the client's doing a lot of the driving here. It's trying to get everything onto the website. And of course, if the client gets interrupted, there's going to be a problem, or at least a problem by our definition. We decided that as a requirement for us, we don't want this state where you can leave the server in an inconsistent state. If the server is just going to start doing stuff with the live website, with the live data, as the client is issuing these requests, then if the client gets interrupted, it could get this inconsistent state, this incomplete version of the website. So we don't want that. What we want is a notion of transactionality for these publish events. Either the publish event happens or it doesn't. That means we want either the before state, which is if anything goes wrong on either the client side or the server side, we want the website to look like it did before, before we did anything to it. And then if it succeeds, it should succeed completely. All of the changes go up. So to do that, the server needs to know when the client has finished a complete description of what it's talking about. So we need one more request in here, and we'll call it commit. The client issues a start request that describes what it has. It uploads all the files, potentially hundreds of files. And then at the end, it says, OK, I'm done. Do what you need to do. And then the server, instead of doing things live to the live data all along the way, it's just going to store these things away. It's going to store away a change description, and it's going to store away the things that get uploaded. And then once the commit comes in, then the server knows that it can start making changes to the live website. I'm going to make one minor modification to this diagram. I'm going to make it look like this. App Engine makes a distinction between user requests, which in this case is requests coming in from the command line tool, and background tasks. They're both executed on your app instances. They're both handled by request handler-like things. But user requests are expected to return quickly, and so they have a time limit of 60 seconds. Background tasks have up to 10 minutes, and of course, they can spawn other background tasks and do an arbitrary amount of work. So most of the work we're going to do, especially if we're acting on thousands of different files, thousands of different data store entries or whatever you might want to be doing, it's going to take a while, and so we need to do it as background work. One of the things to note here is that each of these arrows is an opportunity for the server to return an error code. So if anything goes wrong, if there's a bad request, the client said made an invalid request, or there's some kind of inconsistency, or there's a transient error on the server side, the server can say, just bail and say, look, client, I don't know what to do with this. I'm bailing on this. And then the client can then report that error code to the user. The content developer can see, oh, nothing is going to happen on the website because of this. I'm going to have to fix it or wait for it to be fixed or file a bug report or whatever. And so each of these is an opportunity for the server to return an error without having any changes going live. Nothing has changed the live website until the very end. But the other important thing there is that the commit request is the last opportunity for the server to return an error code. So if it's going to kick off some background work, it has to be pretty sure that that background work is going to succeed. Once the commit is in, the change is committed, and the client is just told, oh, OK, the commit is successful. I don't have to worry about it. It will eventually go live on the website. So we need to accommodate that as well. So to summarize the publishing protocol, we have a start request that starts a change with a change description. We upload the files we need, and we have a commit request that says, OK, this is what we need. You might want an abort request in there, too. In our case, abort just means clean up all that stuff you stored. It's not really going to impact things to have an uncommitted change just sitting around. It's just going to be some extra data. But it's a nice cleanup, and sometimes the client does have the opportunity to issue an abort request. Of course, it doesn't always have the opportunity to issue an abort request. It could be failing because of a power outage or a bug in the client. That sometimes happens. And so it's good to have a scheduled task, a cron job that goes in and aborts stale changes as well. OK, so we've got client-server interaction. We said we wanted it to be authenticated. Let's talk about that part. There are a bunch of different ways of doing authentication. App Engine has had for a long time server-side capabilities to make it easy to implement web services with OAuth for authentication. There's a new way, though, that's, I think, really cool and really important. It makes it really easy to do this very common thing of setting up a web service in different ways, and it's called Google Cloud Endpoints. The difference between writing your own and using Google Cloud Endpoints is that you get all of the features that normally accompany any other Google web service using the same infrastructure can apply to your web service, whatever it may be. And you just set that up as an App Engine application, and you get all that infrastructure built into it. So it's got server libraries for the Python and Java runtime libraries. We're going to use Python today. And client libraries for practically everything. If you've called a Google web service before, you've probably used the client libraries. You've seen we have like a dozen or so of them in all these different languages. And you can use the very same client libraries to make authenticated requests to your own web services. So that's what we're going to do today. This makes it especially easy to set up backends for mobile applications, both Android and iOS. They have full libraries and documentation for making these authenticated requests. Makes it really easy. And also for rich web applications, if you've got a rich JavaScript app that's making requests back to your server. Those are especially easy with the given documentation and libraries. We're going to be doing something slightly different, but still entirely possible, which is to use a command line tool to make the same kind of authenticated requests. And we're going to write that in Python. So I have a lot of slides here on endpoints just because it's kind of the new thing. I'm going to speed through them really quickly. Let me know later if you have questions. I have other things I want to get to. But basically, you're setting up a server. A service has methods, and methods pass these messages back and forth. They get a request in and a response out. So you can just set up these messages as proto-RPCs in sort of a general purpose way here. You can see they're modeled. If you've done any work with ext.db or ndb for modeling data in the data store, this is a similar kind of thing. You're modeling these messages, and you get sort of typed fields and things like that. In this case, the word start here is just our start request. It's the name of our method. And so I've got a start request and a start response that we pass in the project prefixes and the upload paths, and we get back a change ID, which we can use in further interaction with the server as we go through the change protocol for the uploading of the change. So messages can be defined as proto-RPCs. I did want to call out here that a really common thing to do with these messages is either a message is coming in that describes a data structure that you end up storing in the data store, or oftentimes the user has made a request for some data in the data store, and that's coming back out in its basically identical structure as the way you're storing it. So if you're doing that just with proto-RPCs, you've got some redundant code in there. You're describing the data structure for the data store, and then you're describing the exact same thing in your message. There's an open source library called Endpoints Proto Data Store that lets you just take the NDB model and use that as your message structure. So definitely look at that if that's what you're doing, and you usually are. I'm not going to use it in my demo today just because I'm going to do something slightly different in the way we create the data store entities, but it's a really useful library. So here's the service. Again, I won't go into too much detail, but you can see a service is just a class. It extends the service class. We have a decorator that adds some information about it. We'll talk about client IDs in a moment. The service class has methods that just represent the methods of the service. So here's how you do the start method of our service. Again, we've got a decorator describing the request and response data structures. And then the method implementation just gets a request object, builds a response object, and returns it. Here is how we do authorization. So at this point, because we have an authenticated API, and we'll talk more about that, but by this point in the server code, we already know who the user is. So the user has authenticated with the client has grabbed credentials to act on the user's behalf, and now this message already has the user information associated with it. So that's really easy to get out of the library and start doing this. I'm comparing the email address with a fixed list of known content developers in this case. You can get as fancy as you want with access control lists. If there's an error, I just raise an exception, and this is one of the exceptions that comes with the Endpoints library. Notice that when we modeled the response message, we did not even think about errors. Errors are handled entirely by the library, so when you just raise one of these exceptions, Endpoints knows to set the HTTP status code appropriately. You can add arbitrary text messages to that. You can define your own exception classes. It's all built in. And here's just an example of building a response and returning it. To actually set this up in the server, we're going to create, this is basically the equivalent of a WSGI application. If you're using web app or anything else in Python to set up an app, you're going to create the same kind of thing here. This is how you get that from the Endpoints library. And this is how you map it into your app.yaml file. The URL here, it has to be exactly this. It's _AH/SPI/.star. That's not a typo. That's SPI. You'll see AH API in a few places, but here it has to be SPI, and that's just referring to that app variable that we set, the module global. Okay, so client IDs. Every client uses an ID. And not to be confused with user IDs, of course. This is the client ID. We're going to have one client, which is the command line tool. The client has to identify itself in order to act on behalf of the user. So the user signs in and gets permission and so forth. To get these client IDs, you use the Google API console. Again, just like with any other Google API. And so here's one way to get to it, developers.google.com/console. Here's what it looks like. I'm not going to go through a full console demo, but I will just really quickly talk through the process. You create a project. Under API access, you create a client. And when you do this, it'll give you some options as to which kind of client you want to create. All the clients are basically the same. It just sort of changes the way the console interacts with you. And in this case, even though it's a command line tool, we're going to create a web application client. It's a little bit confusing, but we need that because we're going to edit the settings, and we're going to set the authorized redirect URIs like so. To do that, we do this because we want it to interoperate with the development server as we're doing local development. So this is an easy way to do that. Just add localhost 8080 and localhost 8090 to the redirect URIs, and that will get it to work with your local development server. Don't forget to add your actual website as well. And so on the server side, we've got those client IDs in that annotation. We're just going to set that client ID. That's the client ID that comes out of the API's console when you create it. I've also added a second client ID here. This is for the API Explorer. This is a feature of Endpoints that makes it really easy to test your service without writing any client code. This is a built-in general-purpose client for experimentation and trying things out. So you add this ID to the list of clients that the service is expecting, and you can use this really powerful tool. And it's so powerful, I want to demonstrate it. So here's the URL you would normally use. This is for a development server. It's API Explorer. I've got a development server running for a little service right here. I'm going to open a browser. Go to localhost 8080 API Explorer. Did I get that right? This does require an internet connection because it's getting the API Explorer JavaScript code from a live service. But what it then does, that JavaScript then calls localhost. You saw there's some requests there. And what it's actually fetching is the discovery document. You might have seen discovery documents in interacting with Google APIs. It's a description of the machine-readable description of the API that it can fetch directly from the service. And so it knows from the endpoints annotations, the decorations that we made to the class and the methods, that we have a site publish API. I can click on this. And here are the methods. I've got a start, an upload, and a commit. I didn't implement abort in this case. I'll click on start. And I get this cool little request editor. It already knows the structure of the request fields. And so I can just do this. And let's add some upload paths, bar HTML, maybe add one more, baz.png. And so we're creating a change description. This is calling the start method, and I click execute. And you can see it's called the service locally, and it sent it this request, and I got back this response, not authorized, because I have not authorized this client to act on my behalf when interacting with this service. So I go back, you can do that, go back up here, click this little switch, And I say yes, authorize for these scopes. And now it's going to make me go through the sign-in flow. It's opened up a little browser window. I'm going to sign in with my Google account. And I am using two-factor authentication. I hope you are too. Now it's signed in. That little switch has turned blue. It's turned on. Now I can click Execute. And there's the request again, and I get a response with the change ID. So it is now interacting on my behalf with the service on the local development server. And these are screenshots in case that didn't work. All right. So the client, we're going to use the Python client. This is where you go to get all those cool client libraries. The client, I mentioned the discovery document, and for the command line tool, we're actually going to generate the discovery document locally, and then just have that discovery document in a file, so the client doesn't actually have to hit any service to figure out what service it's interacting with. The client library is then going to generate a language-native API to the client code based on that discovery document, and then the library, of course, includes some extra tools to make OAuth easy, so we're going to see that. So here's how you generate a discovery document. I won't talk about too much detail. This tool is included in the App Engine SDK. It's called Endpoints config. I do want to point out you're probably going to want to make two discovery documents, one for localhost and one for your actual server. And when you do that, there's a little bit of a sharp corner here. You have to manually edit the localhost version of the discovery document to replace HTTPS with HTTP. That's how you get it to work with localhost. But that hostname parameter is how you can generate different versions. And so this is client code now. It's Python, but it's client code. We're loading the discovery document, and then we're just passing it to the API, the client API, get the service object out of it. To do the authentication, we can do something like this. What this is going to do is it's going to prompt me to sign in. It'll go get credentials from the service, and then it's going to save those credentials in a file. And then subsequent runs of the command line tool, I'm not going to have to sign in again. It's already authorized to do that. So I can use the tool multiple times without having to sign in over and over again. I get this wrapped HTTP object at the end. And then when I actually call the service, I just call the start method, which is, again, generated from the discovery document. That is my start method. Off the service object, I get this request out of it, and then I can execute the request with our wrapped HTTP object. I get back a response, and I can access the change ID like that. And so real quick for that. Here's the server on the left and my command over here. Notice that when I ran the command line tool, it went back to the browser. This is how it prompts me to sign in. It is actually sending me to Google to sign in. You also notice that I've already signed in because I did that, signed in to Google for the previous demo, but I still need to authorize this client to act on my behalf. So I'm prompted to do that. I click Allow Access. And control returns back to the command line tool, and it finishes what it's doing, and then it gets back a change ID. So now the command line tool is interacting on my behalf with the service locally. And the only change I need to make there to use the live service is to use a different discovery document. Okay, so we have a change description getting to the service. We have a way of communicating with the service and doing the start, upload, and commit calls. Now we need to figure out what to do next. We need to store that change description somehow. So let's store it in the data store. The data store is schemaless. We're going to use the NDB library to actually model this data so it's got a consistent structure. And this is the structure we're going to use. Basically, we store our project prefixes and our upload paths. And we have some extra fields. We definitely want to record who does what. You're going to want to go back and see who's made changes to your website, very sure. And then we're going to keep track of whether this change has been explicitly committed or aborted. One specific thing we want to talk about with changes, later on we're going to need some way of ordering changes. What we want is to promise to the user that changes show up on the website on a first-come, first-served basis. And so to do that, we need to know who came first when these changes have been created. A couple of ways you might try to think to do that. Maybe we use a date time. We generate the date time that it comes in as a field, and then we order by date time. That's probably not the best idea if you really need strict ordering, because the date time is actually set from the system clock of the app instance, and different app instances are going to have different clocks. There's going to be a clock skew of as many as minutes when you do it that way. So you probably don't want date times if you want strict ordering. Another option is to let the data store come up with a system ID when you create the change record. It can do this if you don't set a key name. It'll come up with its own numeric ID. These are generally increasing IDs, but especially if you've got two entities that are not in the same entity group, the system IDs are not guaranteed to be in monotonically increasing order. The different shards of the data store are going to have different allocated ID ranges, so it'll be guaranteed to assign unique system IDs, but not necessarily increasing system IDs. If they're in the same entity group, you get something closer to monotonically increasing, but it's still not guaranteed by the data store. So our idea here is to keep track of our own change IDs. We are going to store the next change ID, and then we're going to update it whenever we create one of these things. Of course, we need to update it transactionally. We're going to need to use a transactional primitive of the data store in order to make sure that two changes don't get created with the same change ID. So there's going to be a singleton data store entity holding the change ID in the data store. This is a really nice opportunity. We do need a transaction here. This would be a great use for a feature that came out about a year or so ago called cross-group transactions. Now, you might be familiar with how data store transactions work. Entities are created in entity groups, and a transaction can execute over multiple entities, but all those entities have to be in the same entity group. You have to know that ahead of time as you're modeling your data, what is going to be changed in the same transaction. And so this new feature allows you to actually use up to 5 entity groups in a single transaction. Now, in terms of scalability, 5 isn't much different from 1, but the cool thing about cross-group transactions is they don't have to be the same 5 every time. You can actually decide which entity groups are involved. And the data store will take a little bit of extra time. It's a little bit slower, but it'll make sure it can meet all its consistency guarantees as it's making changes of up to 5 entity groups when it does that. So you can have the change ID in one entity group. You can create new changes in other entity groups and then just sort of loop those two together in a single transaction as you're updating these things. And you get basically the same effect. But in our case, it's not going to make that much of a difference. You do have to think about your actual throughput needs. And how complicated these things are going to be. And in our case, we're talking hundreds of content developers, not hundreds of thousands. So we decided, OK, let's just put everything in the same entity group, and then we don't have to worry about cross-group transactions. In our case, that turned out to be fine. We have to basically serialize updates to this entity group now, because there will be contention for this entity group as people are making changes. But that's going to work for us, so we're just going to do it. If you're doing custom keys, remember you're using a string value, not a numeric value. And so in our case, we pad with zeros so that the strings will be orderable in alphabetical order and represent the actual change orders. This is how you'd model it in NDB. No surprises here. These are just the fields. I'm going to skip past this. So the content, we now have to store the content somehow. A couple things to think about when modeling the content. Remember, we've got this view request that needs to be pretty fast. We want the view request to come in, grab the data, and serve it, and we don't want to think too hard about how that happens. So as a general rule of thumb, we decided to say, OK, this view request is coming in. It has some information it knows. It should be able to get everything it needs from the data store and then return it to the user without performing a query. It's not strictly necessary, but it's kind of a nice rule of thumb. So in this case, the view request knows the URL path, and so that means at some point we're going to need some data store entity keyed off of the URL path so it can get that thing and then figure out whatever else it needs to do, as opposed to performing some kind of a query. One of the nice things about this rule of thumb is that it's really easy to imagine what the memcache layer is going to look like. If you're going to add in caching, then you can just cache these entities directly into memcache, and then those same gets can occur on the memcache just as they would on the data store. But we also have to remember that publishing needs to be able to store new content separately from the live content. So if it's just a single entity keyed off of the URL path, then when you're creating another one of those, that has to live side by side with that before it gets switched into the right thing. So one idea, again, there are many ways of doing this, but the one we went with was to use a separate entity called a path entity keyed off of the URL path, and then that contains a pointer to a content entity. So it looks something like this. One obvious disadvantage with this is that the view request now has to make 2 data store calls, which you may not want. Not only that, but it has to make them in series. It has to get the path from the URL path, and then it has to wait for that to come back to know how to get to the content object. There are going to be advantages to this design later, so this is actually something that we lived with, but that is a disadvantage if you go do something like that. So what about entity grouping? Do we need to think about transactionality for anything like this? So one idea, the one that we used, is to have one group per path, and then that group contains the path and multiple content objects. And that allows us to set the content key. We can change that pointer and manipulate content objects in a single transaction. So it looks something like this. Here's your entity group. It's pointing to the old content. New content comes in, and then in a single transaction, we can flip that pointer and delete the old content all at the same time to make sure that that's guaranteed to work together in a single transaction. Here's the model for that. Not a big deal. So how do we talk about, let's talk about the apply phase a little bit here. This commit comes in and we've got some work to do. So what exactly happens? Well, the client calls the commit method. It's got a change ID, so we know what change we're applying. The server has two things to do in response to this. It has to update the change record to say, yes, this is now committed, and it also has to kick off some background work. Now, if those two things happen separately, there's always a potential for one of them to succeed and the other one to fail. So if you're updating the change record first, then maybe you update the change record and the server now believes that change is committed successfully, but it hasn't actually successfully updated, added a task to the task queue. Or if you did it the other way around, then it could be applying the change but not realize that it's actually committed it. So what we can do here, this is the justification for a really important feature of task queues. You can add a task to a task queue as part of a data store transaction. So we are going to change the change record, we're going to update the change record and set the apply task in a transaction. That means if the transaction succeeds, both of those things have happened. If it fails, neither of them have. And then we can return an error to the client, and the client knows that nothing is going to change to the live website. So the apply task, and then if it needs to, it can spawn more tasks. And then you've got all these tasks on the website. What guarantees that those tasks are actually going to complete successfully? Well, the task queue does. The task queue actually will drive and retry those tasks until they succeed. So that's basically our guarantee. Once we have committed the change and told the client it's committed, the task is already on the task queue, and the task queue can figure out how to make sure everything works the way it's supposed to. One more thing we need to talk about. Say change 1 comes in and enqueues some tasks, and change 2 comes in, modifying the same file that change 1 does. And both of those get enqueued to the task queue. The task queue does not guarantee a first-come, first-served order when it's executing tasks. So it's possible for the apply phase of change 1 to happen after change 2, and that's going to violate our expectations. So what happens when these things happen out of order? Well, we take care of that by ordering the changes. This is why we ordered the changes in a strict order, because now we can store the last change ID that's affected a path with the path. When change 2 comes in, it updates a path and tells and as part of that, it says, I am change 2. Change 2 was the last person to touch this. So when change 1 comes in, says, I also need to touch this. Oh, wait, change 2 has already been here. I'm going to just return success without actually doing anything. And then change 2 continues to win. It sticks. In this way, the apply phase only rolls forward in our change history. And so that's how we assure that these things are going forward. One minor design detail we need to account for is the deletes. Normally you would think, oh, well, something comes in, wants something deleted, you can delete the path and the content. But in this case, we actually need to remember which change made that delete. And so we're going to have deletes represented in the system as tombstones. The content objects can go away, but the path object can't. The path object is going to stick around and say, yep, I am deleted, and this is the change that deleted me. And that way, we can make sure that deletes stick in the same way. So, to summarize what we've seen so far, and that's basically all the time we have, so I'm just going to summarize what we have. We have a content management system. We've got this sort of remote publishing capability with this general transactional guarantee with eventual consistency of application of changes. So when things go up, they're sort of as guaranteed as possible to go onto the website. We can have arbitrary change sizes, so we can have many thousands of files. I want to put a little asterisk next to that, because if you do implement something like this, you're going to find bottlenecks. You're going to have various places where change sizes are going to be limited. I'll give you one example from what we've just seen. We are creating these change records in the data store, and they describe every file in a project. That change record is stored in the data store, which means it has a 1 megabyte limit. And so that's going to be a limiting factor on change size. And if we get to the point where we need changes larger than that, we could engineer around that. We could figure out other ways to represent changes in the system, that sort of thing. You engineer around any bottleneck, but you usually do it, you wait until you hit the bottleneck. You wait until you need something more before building around it. We are able to get easy authenticated web services using Google Cloud Endpoints. We use the data store for transactional data storage. We use the transactional primitives to implement the full protocol. We used NDB for Python for modeling the data. And we used the task queue for background tasks. We didn't really talk about caching that much, but you can use memcache as your caching layer. That's a service of App Engine. But more importantly, NDB can take care of it for you. You don't have to think about the caching interactions. You just set a cache policy on your data store entities, and NDB will figure out what goes in the memcache and how it can manage all that stuff quickly and easily. We didn't say anything about large object storage, but I did mention that the data store objects are limited at 1 megabyte. On the website, we do have document objects larger than a megabyte. And so what do we do with that? Well, we put them in cloud storage. And the feature of cloud storage, also known as blob store, makes this actually generally invisible to both the content developer and the end user. I can handle that all inside the protocol implementation details, and then the view request is just another URL on your website, and it just knows internally to go to the Google Cloud Storage to serve those things. So you've probably seen, you know the URL for developers.google.com. I did put together a small demo of this protocol in a little project in GitHub. I actually do not have the finished code uploaded there yet, but check back in a few days and I'll have the full thing there if you want to try experimenting with that. It is demo code. I want to stress that. There may be bugs and things. Please feel free to file bug reports. I'll try to brush it up. I actually do kind of want a nice open source version of this, but there's that. If you want to go to the book's website and see more information about the book, that's the URL there. I also have a plus page for the book, and I can also be followed on Google+. One more thing about the book. I am doing a book signing at 3 p.m. today out in the cloud area. We have a limited number of free books to give away, so if you want to show up at 3 p.m., we'll see if we can accommodate you. I'd be just happy to meet you, and I'd love to hear what you're building on App Engine. If you have any questions, we have 4 minutes left for questions, so we have microphones. You can come up to the microphones and ask questions. Otherwise, thank you very much. I'll take the one in the back there first.
Hi, you mentioned that you can have a clock skew of up to several minutes between various App Engine instances.
Yeah, there can be a clock skew. I picked the term several minutes kind of off the top of my head. It's sort of what I've been told in the distant past about it. I think the main thing is that there's really no guarantee of synchronicity of the clocks between them.
Yeah, the question I really had is how the logging service deals with that.
That's a good question. I can look into that for you. I don't know if there's like a separate service that's actually logging that or if it's getting the system time.
Seems like kind of an important...
No, yeah, exactly. No, that is very interesting. We can ask at the cloud booth and we'll get a definitive answer for you. But I know that like a lot of the logs are managed by a service, so that can sort of come up with its own source of time, but I'm not sure.
So cool. Great job. This stuff is awesome. But a question for you: are you using the App Engine full text search service?
That's something I did not have time to talk about.
Okay.
But yeah, absolutely. If you're building a content management,
is it going to be in the sample code?
I would like to add it to the sample code. It's not in yet.
Okay, cool. So were there any challenges that you found with using full text search API?
Not really, actually. It worked pretty much the way you would expect it to. They do a really good job of synchronizing data store entities with the documents in the search index. We have a couple of basic ways to get our documents into the search service, but it was pretty straightforward kind of to the terms of the search API.
As far as your method for for indexing the documents, did you fire off a task after the commit phase to add it to the search index? Or did you do it as part of the entire transaction? Or did you do it separately from the transaction?
Right. So one of the nice things about the apply phase is you can do basically an arbitrary amount of work, and it gets sort of driven to completion by the task queue. So yeah, we do at some point in the publishing process, in the apply phase, manage the updating of the search indexes. Okay.
But I'm asking, is it separate from that transaction? So in case search fails, indexing fails, does that block the transaction, or is it a completely separate task?
Well, you can define those parameters yourself based on how you write the task.
Right.
If the API call fails for whatever reason, you can decide whether that's fatal to the task and needs to be retried.
Right. I was just wondering what you guys did as far as, did you decide to fail the task or fail the transaction or just let it slide?
We have a bunch of things. I don't know about the search API specifically, but there are a couple of cases where we've had to make that call, say, okay, well, this is, we just want this to, the task is successful even if that one thing didn't happen. There are a couple of sort of residual changes we make to our data structures that work kind of like that, so yeah.
Awesome, thanks.
Yeah, go ahead.
Sorry, I'm back. Did you just say that the blob store is really cloud storage?
They are separate, but the APIs are similar.
Okay.
So that's why I didn't want to make much of a distinction between them. The implementation we used predates the cloud storage that has the same API as the blob store, so we use blob store for the actual thing. But you could easily use cloud storage for that.
Okay, thank you.
Anyone else? Okay, cool. I'll see you out there. Thanks very much.